So until now we have considered the semiconductor in equilibrium and determine the electron and the hole concentration. We will until now we have determined the electron, what is the electron concentration, what is the hole concentration inside the semiconductor is in equilibrium condition. In the conduction band and the valence band, whenever we are trying to find the electron concentration, that electron concentration always be calculated into the conduction band, and whenever we are trying to calculate the hole concentration, that will be always into the valence band. So that we have calculated so far. Now the knowledge of these densities or the charged particles is important towards the understanding of the electrical properties of a semiconductor material. Now why it is important? Because the net flow of the electron and the holes, that means that the net flow of carrier or the electron and hole ultimately determine the current inside the semiconductor. Okay, so that's why it is important. The process by which this charged particle is moved, that phenomenon is called the transport phenomenon. Here in this chapter we will discuss the transport phenomenon inside the semiconductor, how the carriers within the semiconductor move. So that is the process of the carrier transport. So here we will consider the two basic transport mechanism inside the semiconductor crystal. First one is your drift and second one is your diffusion. Okay, this is the two basic transport phenomenon we are interested in our syllabus. So whenever we are trying to understand the drift, now what do you mean by the drift? In a nutshell, drift can be understand with the help of movement of charge carrier. So drift is actually the movement of charge carrier due to electric field. So that is the definition of the drift phenomenon. So whenever there is a electric field applied onto the semiconductor, and for the application of this electric field the charged particles moves inside the semiconductor, then this phenomenon is called the drift. That's why with the application of the electric field the charge carrier move inside the semiconductor and generate some amount of current. So that current is also called the drift current. And next is your diffusion. So what is the short definition of the diffusion? So diffusion of the carrier, or diffusion is also the flow of carrier, and that is happens due to concentration gradient. So if there is two region inside the semiconductor, this is region 1, this is region 2. So concentration of carrier in region 1 is higher and the concentration of region 2 is lower, of the carrier is lower. Then there is flow of carriers from region 1 and to region 2. So that phenomenon is actually called the drift phenomenon, diffusion phenomenon. And as the carrier moves, there is a generation of current. So this current is called the diffusion current. So this is the two basic mechanism inside the semiconductor through which we are getting the current out of the semiconductor. Now the temperature gradient is also responsible for this concentration gradient. If the temperature of this side is higher and the temperature of this side is lower, so carriers generated in the region 1 will be higher than the carriers generated in the region 2. So then there is a diffusion phenomenon happen inside the semiconductor. Now why the carrier transport is important? Carrier transport is actually responsible for calculating the current voltage characteristics within the semiconductor device, and this current voltage characteristics is important for the further application of the semiconductor device to different field. So that's why we are calculate the drift current and the diffusion current. What is the expression for this, and what do you mean by how we can calculate the equation for this? So carrier drift. Now an electric field applied to the semiconductor will produce a force onto the electron. So there is an electron, and if the electric field is applied onto this electron, then and also the holes. Okay, so they will experience a net acceleration and the net movement provided that there are available energy state in the conduction band and the valence band. So if we apply electric field, electron will always move, but provided that there is a conduction band, there is a free space of the electron to move, and also holes will always move into the valence band. So whenever we apply electric field, hole will obviously move. Okay, but there is provided the condition that there is available state into the valence band. So that is the two condition. So this net movement of charge due to the electric field is called the drift phenomenon. Okay, so movement of charge due to the electric field is the drift phenomenon. We have called this before at the beginning of this lecture. So net drift of charge give rise to the drift current. So that is the outcome. As the electric field applied, there is a drift of carrier, so there is a generation of drift current. If the carrier moves inside the semiconductor, there is a generation of current, and that current is called the drift current. Okay, now the drift current density. Drift current density. If you have a positive volume of charge density rho, positive volume of charge density rho, moving at an average drift velocity Vd. Okay, now so if this is the case, okay, this is the volume charge, and this volume charge is moving with a velocity Vd. Due to the application of the electric field, obviously, until and unless there is the electric field, there is no generation of drift current. So upon the application of electric field, a volume charge density rho moving with a velocity average drift velocity Vd, so there is a generation of drift current density, and this drift current density is denoted by J drift. Okay, so this is the drift current density J drift. This is equal to rho into Vd. So this is the drift current density. Now if we want to know that what is the unit of this J, okay, so J is actually unit of J, you can say unit of J is equal to you can say unit of J is coulomb per centimeter square, or you can say ampere per centimeter square. So ampere per centimeter square is the definition, unit of this J current, and if the current is denoted by I, that current unit is ampere. So from the expression rho into Vd, how the left side and right side of the equal, though you can see that the rho is the volume charge density. So volume charge density is the charge per unit volume. So per unit volume may be centimeter cube, and Vd is the velocity is the centimeter per second. So rho into Vd equal to, so charge divided by centimeter cube into Vd is centimeter per second. So charge per centimeter square per second, and also we know that the number of charge moving per unit time, it is the ampere. Okay, so that's why you can say it is ampere per centimeter square. Definition of ampere is number of charge carriers moving per unit time. So number of charge carriers that is moving per unit time, that is the ampere. So that's why you can say that the unit of J is equal to rho into Vd, that is ampere per centimeter square. So that is the simple understanding this. You must always try to relate the left hand side and the right hand side unit, so that it will be very helpful to identify the what is the loopholes in your equation. If you mistakenly write any kind of error in your equation, then it can be easily identified with the help of this calculation. Okay, so I hope it will be clear to you. So now for the case of positively charged hole, we are considering this rho volume charge density is due to positive charge holes. Okay, so we are considering the positive charge holes, so that's why P for the holes, and the drift current density for the holes is denoted by E into P V d into P. So Vd, that is the velocity, and that is the volume charge density. Okay, now this is the equation for the Jp drift. Now the equation of motion of particle from the Newtonian law of mechanics, motion of particles, we will try to relate the motion of particle with this equation. So motion of particles due to positively charged holes is from the Newtonian law of mechanics in the presence of electric field E. In the presence of electric field E, so there is a force applied onto the particle. So that is MP, effective mass of particle, force equal to mass into acceleration, all of you know that, and that is equal to, also force is equal to, if there is the electric field, force is also equal to E into, this is the basic physics. Okay, so I am again clarifying this equation, that this comes from the Newtonian law of mechanics, that we are considering the motion of particle, that holes. Okay, we are considering the particular holes, and we are considering they are moving due to the application of the electric field E. Okay, now from the Newton law of mechanics, we know there is a force applied onto these holes, and that force is also equal to mass, effective mass of holes into acceleration. That is one equation. And also if there is a charge, we are considering the whole charge as the electronic charge, that is positive E, that is denoted by whole charge, positive charge, and force is also equal to charge into electric field. Okay, you can see this equation from the internet. I am not describing this how force is equal to electronic charge into electric field, but this is true from the physics. Okay, and this is also from the Newtonian law of mechanics, MP into A. Okay, now if the electric field is constant, then we expect that the velocity to increase linearly with time. Okay, so if the electric field is constant, then we expect from this equation, then the velocity to increase linearly with, this is the linear equation, so we want that the electric field is constant, so acceleration will be constant. Acceleration will be constant means velocity is increases linearly with time, because acceleration is velocity per second square. So however, charged particles in a semiconductor are involved in collision with ionized impurity atoms with their thermally vibrating lattice atoms. These collision or the scattering events alter the velocity characteristics of the particles. So as the hole accelerates in a crystal due to the electric field, so there is a hole that is accelerated due to the electric field. Okay, the velocity increases when the charged particle collides with the atom in the crystal. The particle loses most of its energy. This particle will again begin to accelerate and gain energy until it is involved with scattering process. This continues over and over again throughout the process. This particle will gain an average drift velocity, which for low electric field is directly proportional to the electric field. Okay, so what is the meaning of that? That means there is inside the semiconductor, the hole is moving, but the hole is not the only particles present inside the semiconductor. So there is other particle present inside the semiconductor. So what happens is that if his hole is trying to move inside the semiconductor, then it is encountering the collision with other charged particles, so it loses its velocity. So again it is, after loses its energy, it again tries to move with a velocity. So in this case it's gain a average drift velocity Vd, and for the low electric field it will try to obey the equation, and the equation is that V into dp, that is the drift velocity of the holes, is equal to mu p into E. Okay, so this is the mobility of the holes and this is the electric field. That is the equation. Why this equation comes? Because of this understanding, because holes is not moving linearly, because it is always encountering a collision. So if this is a collision, then it will again it is not the only velocity it is gaining in this process, it will again collide, again try to move with a velocity, again collide, again try to move with a velocity. So in this case we are getting a average drift velocity, and it has been found that this average drift velocity is equal to mobility into electric field. So that is the case. So if this is the case, the average drift velocity vdp into mu p into e, so mu p is proportionality factor, is called the whole mobility. So mobility is an important factor, then you must know the unit of mobility. So unit of mobility is centimeter square. You can check this also in centimeter square volt second. Okay, so this is the unit of mobility. So from that equation, jp drift is equal to, we know that E into P into Vd. This is previously derived this. So E into mu P into P into E. So we have replaced Vdp by mu P into E. So that is the equation for Jp drift. Okay. So in this way we can also calculate the equation for holes, that is J in drift. So E mu P, concentration of electrons, into E. So that is the equation for Jp drift due to the holes and due to the electrons. Okay, and this equation is important. This equation is happening because of this average drift velocity comes into picture, and that is proportional to the electric field. It has been found experimentally, it is proportional to the electric field. Okay, and one thing I have mistakenly write here, that means the charge of the holes is positive here and the charge of the electron is negative, that's why minus E will come here. Okay, so and also in this case, for the case of the electron, this drift velocity is replaced by Vdn due to the electrons. So that is the case. Now there is a table for, you must know that is the mobility for electron and the mobility for holes, which one is higher. So obviously mobility is expressed, there is different semiconductor material, gallium arsenide, I am writing these two. So mobility is, the definition is that, the theoretical definition or the not the mathematical definition, theoretical definition is that how well the carrier can move, okay, inside the semiconductor, that is expressed by the mobility. So as we know that the charge of an mass of an electron is obviously lower than the mass of an hole is considered as a heavier particle, so that's why mobility is electron is always be higher than the mobility of holes. So you can remember this with this concept. You can build your own concept, but I have remembered this with this help of this concept, that how well a carrier can move inside the semiconductor, and that is represented by this mobility. So that's with the help of this understanding, as the electron mass is lower, so you can consider the mobility of electron will be higher, it can move with a very higher velocity. So the typical value of silicon mobility is 1350, and for the electron, and for the hole it is 480. And also for the gallium arsenide it is very much higher, that's why gallium arsenide is also used for the high current device or the high electron device, high speed electron device. Okay, and here in this case, for the case of the VDP, I have written that the VDP is equal to mu P into E. Okay, and it has been said that if the electric field is in that direction, hole will also move in that direction, but the electron will move in the opposite direction. That is, you must remember. Okay, that is happening inside the semiconductor. So for this understanding, your VDN, okay, your VDN, and this is not the case. Here at the electron charge is negative, this is E, negative E, carry concentration is E, and this is your VDN, and VDN is represented by electric field is in this direction, holes electron will moving into the opposite direction. It has been experimentally proved. Okay, so that's why it is, that means it is velocity is in the opposite direction. Velocity is a direction, that's why it is negative. Okay, velocity is a direction, it is not speed. Velocity is a vector quantity, it has got a direction, so it is moving into the opposite direction, so that's why negative mu n into E. So your total current due to the electron, drift current, is equal to minus E into n into minus mu n into E. So your total drift current due to the electron is E mu n into E. Okay, so your total drift current due to the electron and due to the holes combined, drift plus Jp drift is equal to E. If we just taken out the E, so mu n into n plus mu p into P into E. So this is the total equation for the drift. Okay, due to the electron and holes both consider. If we consider both this effect, then this will be equation for the drift. Okay, I hope it will understandable to you. In the next class we will discuss the diffusion.